So today we're going to be going through the simplex method. The simplex method is relatively simple. It basically, given some optimization problem, the problem's constraint is going to bring upon a polyhedral, and that's going to be where our feasible solution to the problem is. The simplex method will simply pivot each basis from one point to another, and it continues to pivot until it finds the optimal value. So let's kind of go through a problem first, and then we can develop our simplex method and use that to solve this problem. So suppose we are a factory producers where we produce tables, chairs, and sofas. And we're told that a chair makes $20 worth of profit, table is 30, and sofa is 50. The problem is we have some constraints. Specifically, we have 300 units of wood available, but each chair uses 5, table uses 8, and sofa uses 15. You also have 200 hours of labor available, where each chair requires 3 hours, table 4, and sofa 8. Finally, you also have space to store 30 pieces of furniture. Chair takes 1 unit, table takes 2, and sofa takes 4. So, given this problem, let's first formularize this as a proper mathematical problem. So we have some sets. In this case, our sets is chairs, tables, and sofas, right? So we have products, which is our sets. We also have some data. In this case, the data would be anything that we see are numbers. In this case, we have profits for each product. We have wood required for each product. We have labor for each product. We have storage for each product again. And then we have maximum wood available, maximum labor, and maximum storage. Next up, we want to think about our variable. So our variable is what we get to decide. In this case, we get to decide how many products to make. So it would be XP, where XP is supposed to be an integer for all products that we have. Then our objective is to maximize the profit. So sum over P in P, where we have profit times XP. And we want to maximize this. Lastly, we need to consider our constraints. So our constraints are the ones that forms our polyhedron. In this case, we want to ensure wood is within the region that we want. So wood P times XP is to be smaller than max wood. P in P. We also have labor. So labor P times XP is smaller than max labor. And then finally we have storage. So storage P times XP is to be less than or equal to max storage. So with that, let's now have a think about our simplex method and how it goes about. So let's have a look at the simplex method now. Before we start, let's have a brief look at what the variables and what these stuff relates to. So A in this case is going to be our matrix, constraint matrix. So that's going to be these guys with P, labor P, storage P. They're going to store the coefficients. C is going to store the objective coefficients, so that's going to be profit. So objective coefficient And then B is going to be storing the right-hand side, M wood, M labor, and M storage on the right-hand side. So, yep, okay. And so, starting off, the simplex method is done in 3 steps. We want to determine the entering variable, we want to determine the leaving variable, and then we want to make the swap. What is the basis though? The basis is basically meaning what our current solution is. Okay, so starting off with the entering variable, we're going to calculate this thing called the dual variable. And the dual variable belongs to the dual problem. What is the dual problem? Well, the dual problem is basically a problem that is opposite to what our current problem is. What does that mean? That means our C, so in the dual problem, our C objective coefficient is going to become our right-hand side in the dual problem, and similarly the right-hand side becomes our objective coefficient. The maximization here turns into a minimization, and then our constraints becomes our variable, and our variable becomes the number of constraints we have. So that's the dual problem, and there's a theory that the dual problem, the minimization of the dual problem is equal to the maximization of our primal problem. So we use this to calculate our reduced cost, and that's basically going to tell us for each variable that is non-basic, how much improvement does it bring to our solution. If all our reduced cost is less than or equal to 0, then we stop at the optimal value, but otherwise we want to select the maximum one as our entering variable. To determine the leaving variable, we want to calculate this ratio first. And then once we calculate this ratio, we want to find, okay, which one is kind of contributing the least to our current solution, and then given this ratio is greater than or equal to 0, and if it is contributing less, then we can select that one as our leaving variable. Now, if this set is empty, then that means the problem is unbounded and we can break. If it's not unbounded, we can make the swap and then continue on with the simplex method until we find the optimal solution. So firstly, I'm going to identify how many rows and columns, rows and columns we have in our matrix. From there, I want to determine what our basis is. So basis is equal to list range, and we start off with a basis where all the slack variables are active. Now that's a new term. What the hell is a slack variable? Slack variable are basically variables we introduced. So you see how these are inequalities, right? We introduce slack variables to kind of soak up the remaining function of the left-hand side, and so this kind of becomes an equality. And what does that mean? So, like if M wood was 5, for example, and the left-hand side here is, I don't know, maybe 2. Clearly 2 is less than or equal to 5, which is good. It's not violating our constraint. But to turn this into an equality like that, we just add in a slack variable s. And what the slack variable does is it's going to soak up what remains on the left-hand side. So in this case, 2. 2 plus s needs to be 5, so s is equal to 3. So that's basically what our slack variable is. Great. So we want to initialize our basis with all the slack variables being active. So that means none of these primal variables, xp, will be active. They're all going to be set to 0. Basically, this is going to lead us to the origin as our basis. And then our non-basis, is going to be everything that is not in our basis. So n minus m. Okay, so next up, we want to determine, well, what is this large b value here? Because I never really explained it. This large b value is basically going to be the variables, sorry, the matrix that corresponds to the active basis. So it's going to be b is equal to a, which is our matrix, and we're going to take the ones that are active. And then b inverse is obviously going to just be the inverse of b. Loop dot inverse b. Yes. Great. Now I'm going to initialize a count here to just kind of determine how many pivots I need to be making. And then we can start our simplex pivoting. So first step is to identify y value, right? And we currently have this b value. We just need to transpose it now. Well, what is this cb? Funnily enough, that's just going to be the objective coefficients that that matches up with what our current basis is. So cb is going to be c basis. And then we can compute our y variable, numpy dot product, and b inverse dot transpose with cb. So I might as well put a comment here. Determine the entering variable. So next up, we want to then determine, okay, so we got our y variable, but we need to compute this reduced cost. But hold up, Alan, what is this pj? So pj is basically going to be stuff that corresponds to the ones that are in our non-basis. So it's going to be looking into all the variables that are not in our current solution, right? That's why we're determining the entering variable. So pj is going to equal to a, and then non-basis. And so our reduced cost is going to be c non-basis minus numpy dot our derived variable times our stuff in matrix A, that is non-basic. So that is basically this part done. Next up, I need to determine what is our entering variable, right? So for this part, I will use if np.all numpy.all reduced cost is smaller than or equal to 0, then optimal solution found, and we can just set x is equal to numpy dot zeros n, which is how many slack variables we have. X is going to be our basis then, so we're going to activate the ones that are in our basis. Oops. XB. And we want to return x p dot cx and count how many pivots we've made. Okay, so I'll explain xb just in a bit, but let's continue for now. So Okay, yeah. So now we need to determine what this J star is, right? Because we did this just then, but I need to determine what the J star is, basically the index of our entering variable. In this case, J star is going to be numpy dot the maximum of our reduced cost. And then our entering variable is going to be the non-basic variable that corresponds to this index. So next up, I want to determine the leading variable. What is the leading variable? Well, firstly, we need to compute this ratio, and first part, I guess, is determine what our PJ star is. Again, PJ star is going to be talking about what our entering variable is. That's why we have the J star. And then alpha J star is going to be numpy dot B inverse by P J star. So like that. And then next up is to compute, Okay, so next up, I'm going to make a swap between these two. If alpha J star has no variables that are greater than 0, then we're going to stop. So if numpy alpha J star is less than or equal to 0, then raise value error volume is unfounded. Oops. Okay, cool. And then otherwise, I want to decide which are the positive indices. The alpha J star is greater than 0. And then compute the ratios in P dot divide the positive indices alpha J star positive indices. Great. So we do our division there. Again, XP is not defined, but we'll come back to that later. And then if I suppose I have this code in my cheat sheet, so I'm just going to include that in there. It's equal to 0. So if the number of ratios we have is 0, so there is no positive indices, then I'm just going to do what I did before. So this is kind of redundant, but I don't want to refilm this if this is wrong, so I'm just going to include that here. Okay. So we want to finally determine what is our leading variable then, because we've computed the set and now I need to take the minimum. So R star is supposed to be np.argmin of ratios, and then our leaving will take that dot positive indices, style. Great. And the last thing I need to do is I need to make the pivot. So yes, I do have that here. Do a swap. Okay, so our leaving index is supposed to be basis dot index leaving. Now entering index is basis dot index entering. Our basis is going to be leaving. Leaving index is equal to entering now. Non-basis is going to be entering their index. It's supposed to be leaving, and then I want to sort the bases so they are in order of the columns. So I need these to be in order. And then I also need to sort that for the non-basis. Okay, so finally, I've made the swap, and now I need to recompute our B value and all that. So B is going to be A, where the basis is active. B inverse is going to be the inverse of B, and then XB. Okay, so XB is going to be the dot product between our inverse and our right hand side constraint. And what is that? That's basically going to be telling us the actual value number of values x some value x, so the variable xp, these guys should be actually be taking. So xp dot product b inverse b, and then I can implement the count. Now I haven't calculated this beforehand, so I also need to pop that into here. Okay, so that would be that for this revised simplex algorithm, and I will be right back. So 20 corresponds to $20 per chair, $30 per table, $50 per sofa. 5, 8, 15, that corresponds to the width, 5, 8, 15, and then 3, 4, 8, and then 1, 2, 4. So I've gone ahead and inputted these values in. Also the right hand side constraints, and here are our slack variables, right? So slack variable 1 is only active in the first coefficient, slack variable 2 is only in the second coefficient, and then 3 is only in the third, sorry guys, said coefficient, third constraints. This slack variable also corresponds with 0 value in our objective coefficient. So put zeros in there, and this is going to give me a few bugs. So the first bug is in line 49. And so this should be numpy.where positive indices, and that should be okay now. Python run. Okay, so our entering index should be coming from our non-basis, so variables that are not basic. So there should be non-basis, And let's give that a try again. Okay, so it works. These are our what our values are. So it's telling us we should produce 30 chairs, no sofas and no tables. And then there are some slack variables for the first constraint and second constraint. So yeah, and our profit in this case is $600. Okay, cool. Now some people may realize, hold up, Alan. What if these aren't integers? Because clearly you've stated that these variables should be integers, and what happens if it's not? Because right now everything I've put in here are very linear, right? And that's what the simplex method is for, linear programming. It's not for integer programming. I'll be talking about the integer programming in branch and bound video that may or may not come out. But yeah, go ahead and look into the branch and bound method if you are interested.